Okay, in this video we'll do a short overview of the cache configurations on AMD Zen 2 CPUs, and we'll look at that in the context of the recently launched 3100 and 3300X CPUs, which have the same core counts but different cache configurations. We'll look a little bit at how the cache configuration could affect performance. As is pretty usual nowadays in modern architectures, we have 3 levels of cache in Zen 2. The Zen 2 architecture, like the previous Zen 1 architecture, groups cores into 4 core CCXs. Each CCX, in the case of Matisse and Rome, we have 16 megabytes of L3 cache. And then below that, each core has its L2 and L1 instruction and data caches. The L1 and L2 caches in Zen 2 are inclusive. This means that when we write a value into the L1 cache, we immediately write it into the L2 cache as well. So the L1 and L2 caches will always have the same data in them, or at least all of the data in the L1 will be in the L2. Of course, there might be more data in the L2 that's not actually in the L1 anymore. The L3 cache is shared between all the cores in the CCX, and it's a victim cache to the L2 caches of the cores within that CCX. So when a piece of data gets evicted out of the L2 cache in any of these cores, it'll get bumped up into the L3 cache. And that'll happen from any of the cores within the CCX. It's important to note that we can't evict something out of a L2 that's in CCX 0. We can't evict it into CCX 1. So because also there's what's called the write-back policy for the L2 and L3 caches in Zen 2. Essentially, the L2 and L3 caches are not necessarily updated into system memory unless we give what's called a write-back command. So we actually tell the cache to say write data, write address A back into system memory. So the L3 cache might not actually have the system memory might not have the updated data of the L3 cache all the time, and this helps reduce the usage of the memory bus. So like we said, it's important to notice that the L3 cache is not shared between CCXs. So in the case of the 3300X, where we have a single CCX with 4 cores and 16 megabytes of L3, we have the full 16 megabytes in this L3 available to the cores. So if we have a thread in core 0 here that's throwing lots of data out of its L2 cache, we can fill up a full 16 megabytes. Now if we go to the 3100, we have still 4 cores, but we've cut off 2 cores in each CCX, and we have a total of 16 megabytes of L3, so we actually only have 8 megabytes of L3 in each CCX. Now you'll notice that if we take the same core 0 and start kicking data out of its L2, we can only fill up 8 megabytes, and we can't fill up the other 8 megabytes of L3. So actually the 3100 will only basically act like it has 8 megabytes of L3 to any single thread. And you'll see that in a lot of reviews that the 3300X performs way better, especially in some single-threaded workloads, because those workloads actually use quite a lot of cache and will throw data into the L3 and want to use it again. And so if you only have the 8 megabytes of L3, you'll start to have to push this back to system memory, and then you'll have the whole memory latency to deal with rather than being able to go backwards and forwards onto the L3 with a full 16 megabytes. Now, another interesting thing to note is that the because we have two CCXs in general on Zen 2, or we have multiple CCXs. Now, say what happens is we have an address that both this core 0 here and core 5 are working on. Now, when, say, core 0 updates some address here into, initially it's L1 and L2. Of course, remember the L2 is inclusive. Now, in address A, we've written to some new value, so we say written 1 instead of a 0. Now, of course, if that data is then still in address A, in system memory will still be a 0. And if address A is still here in the L1 and L2 of core 5, A will be also a 0. But here, of course, we've written a new value, A is 1 here. So now we have a problem that not all of the addresses are not all of the data in this address is the same. So what we need to do is we need to reflect this value over into this cache and over into system memory before core 5 can continue working on this piece of data. So potentially you have to wait for data to get thrown from one core to another. However, it's not very clear whether whether data is actually being transferred directly from one core to another. It would seem like the latency, based on testing done by mostly AnandTech, you'll see that the latency of what they measure as between two different cores is actually the same as the memory latency when you go off the CCX. So there's a possibility that actually it's just pulling this data off straight out of the memory rather than across the cores like this. It's going straight out of the memory into the other core. And in this case, what happens is we have some write back instruction is done first to update this to a 1, and then the other core picks up that data. And this might actually happen in the memory controller. There's some kind of a buffer, but it's quite suspicious that the latency we see in those instances is actually the same as the memory latency, because it would actually suggest to me that it's not actually relevant to measure the latency between cores in that way. And anyway, it doesn't make sense to me from a multi-threading perspective to have data on different cores like this that is dependent on each other. It would make much more sense to, rather than doing it first a bit here, right, and then doing a bit here with that data, it would make much more sense to me to just do it here. And because this core is going to have to wait anyway, it's going to do that. If we look at time like that, is actually going to have to wait until here before it happens in that core. Why not just do it serially, one after the other, in the same core? And then you take advantage of the cache locality because it's already, all your stuff has been put in this core. So it would seem like, actually, to me at least, it doesn't make sense that we would throw data across cores like that at all regularly. And I would suggest that actually the main limitation of the 3100 and some of the other Zen 2 CPUs is actually that we have this only 8 megabytes of cache in the CCX rather than the full 16 gigabytes. So I hope that was interesting. Like I said, if you object or have some information that some useful information that would suggest otherwise, then comment below, and I guess like or dislike the video, and subscribe if you're interested in occasionally more content like this.